Okay, we're going to get this started now. Okay, tonight's keynote talk will be about the X3 ion drive hull-based propulsion system project between NASA and the University of Michigan Engineering Department. Dr. Jorns will discuss the developments to date and some of the future uses of this propulsion system. Professor Benjamin George received his bachelor's degree in physics from Yale in 2007 and his doctorate from Princeton University in 2012. His work is focused on investigating nonlinear wave processes for improved ion heating in low-temperature RF plasmas. In 2013, he joined the Electric Propulsion Group at the Jet Propulsion Laboratory as a technologist. His research at this institution included theoretical, experimental, and numerical studies of low-temperature plasma instabilities and their role in operation of hollow cathodes and Hall effect discharges. In 2017, Dr. Jorns became a member of the faculty at the University of Michigan and was named the co-director of Plasma Dynamics and Electric Propulsion Laboratory, or the PEPL. As co-director, Dr. Jorns manages the day-to-day operations and supervises the thesis work of all the doctoral students. He has oversight of over the 6 major test facilities, the lab diagnostic suite, and research direction of the group. Since his start at U of M, Dr. Jorns has worked to expand the analytical, numerical, and experimental capabilities of PEPL, particularly for the purpose of fundamental plasma dynamic studies. Examples include the implementation of high bandwidth, time-resolved laser-induced fluorescence systems and a coherent Thomson scattering diagnostic for measuring plasma turbulences in Hall effect discharges. His scientific contributions to date include examining nonlinear wave interactions in low-temperature plasma, discovering new gradient-driven self-organized structures in Hall discharges, developing models for the anomalous effects due to acoustic turbulence in the plumes of high-current hollow cathodes, and examining the problem of turbulence-driven transport in ENB devices. Recently, he has started to explore machine learning techniques for overcoming the current modeling impasses facing the electric propulsion community. Ladies and gentlemen, let's give a warm welcome to Dr. Benjamin Jorns.
I'm going to try to cover all of those topics today. There will be a quiz at the end, yes. Thank you.
Great.
That's right.
I was told there would be no math.
Well, that was why. There'll be. No, I do appreciate this opportunity to speak to all of you. It's nice to be in a room with fellow space enthusiasts, so I'll assume this is a friendly audience. I did recently come from an Air Force review where that was not the case, so please be kind. Yeah, my name is Ben Jorns. I am an assistant professor at the University of Michigan, and it was mentioned I'm the co-director of the Plasma Dynamics and Electric Propulsion Laboratory. To give some context, this is the second oldest laboratory that does electric propulsion research in the country. And it was not in fact founded by me. It was founded by Dean Alec Gallimore, who is the Dean of the Aerospace Engineering Department. So many of the programs that you'll see that are initiated here, specifically X3, comes from his mind. I've just taken over management of it and some of the research direction in the past 2 years. Today I'm going to be talking about a technology specifically designed for the purpose of expanding our grasp beyond Earth's low Earth orbit. And in particular for looking to potentially crewed exploration of Mars. And that's this thruster right here, which is called the X3. It's an experimental thruster, X, and three for 3 channels. So there's a clear designation right there. I'm going to talk a little bit about how it works and why we are interested in it and ultimately some of the challenges. But I think it's important to give some context to the research itself, which is this. This is a relatively recent roadmap that was published by NASA just a couple of years ago, talking about the major technological milestones that need to be accomplished on the way to sending crewed exploration to Mars, and by that I mean people. You can see it's a little hard to make out with the text here, but some of these are already in flight. For example, the International Space Station, the argument being that this is a platform from which we can learn how people live in long-term in space. And there's some near-term goals like the space launch system. And then ultimately, when we get to Mars, things like crewed capture and robotic exploration to try to figure out things like landing sites. But right in the middle here, you can see it was called out explicitly is this thing called solar electric propulsion. And this is a next generation technology which contrasts to kind of the chemical rockets that we're more familiar with, the things you see that have been used to launch the space shuttle, for example. Solar electric propulsion has been identified as a critical and so-called key enabling technology for the future exploration of space, and specifically in this context for crewed exploration of Mars. With that in mind, in the past 3 years, NASA has initiated a research program under this auspices of this name right here called Next Step. And the goal of the Next Step program ultimately is to explore different technologies for the 10 to 20 year horizon that could ultimately facilitate things, as I said before, crewed exploration of space, and looking in particular at the propulsive technologies that would serve as the mechanism for driving the space capsules on their way to Mars. With that in mind, in 2016, there were 3 different thruster concepts or propulsion concepts that were selected by NASA for further study. This one in the upper left-hand corner is called Vasimir. It's an engine that is developed by a company called Ad Astra based out of Houston. The lower left-hand is a concept from the University of Washington and a company called MS&W, the Electro-Lorentz Force Thruster, or aptly named the ELF. And then on the right-hand side here is the technology that I'll be discussing today. This is the XR100 system, which leverages the thruster that we have at Michigan called the X3, or the Experimental 3-Channel Device Configuration Thruster. Now, I'll mention that the Next Step program contract was awarded to Aerojet Rocketdyne, which is a commercial manufacturer of space elements. And Aerojet Rocketdyne has been managing this contract. The University of Michigan is a subcontractor providing the actual thruster itself, whereas Aerojet Rocketdyne provides the support elements like the power processing and flow systems. And NASA plays a key role in not only managing the contract, but ultimately providing technical guidance and test facilities, which I'll allude to later. So you can see the collaborations listed up there in the right-hand corner. In the lower left-hand corner, this is the X3 thruster, and it's mounted in one of the large test facilities at NASA Glenn Research Center. This is a picture taken from 2017. And you can see that ultimately when this thing is operated, it's fired downstream in a vacuum test facility. So we pump the air out of that system and fire the thruster, trying to demonstrate things like performance. So the X3 system, to give some context or framework to this discussion today, I want to talk first about why we selected the X3 and why we think it's a promising technology for these ultimate crewed exploration demonstration missions, what work we've done to date, specifically at the University of Michigan, and then ultimately moving forward, what are the challenges we envision for this technology, not only in the near term, but for this 10 to 20 year time horizon. So why this technology? Well, there are 2 reasons. Number 1, the X3 is a type of electric propulsion. And number 2 is it uses or is based off of a heritage technology called Hall effect thrusters, which have a very high demonstrated performance and maturity, and therefore we have confidence that the X3 will work quite well in space. So I want to break these 2 different elements apart, piece by piece, and talk ultimately how they relate to the motivation for using this technology. So the first one is the X3 is a type of electric propulsion underlined. Okay, well that begs the question, what is electric propulsion? And frequently when I start my class on electric propulsion, I pose this to the questions, and these are the answers that come out. So when people think electric propulsion, they think the Starship Enterprise, a destroyer, or my personal favorite, the battleship Star Galactica, right? Ultimately, of course, electric propulsion is not this next generation technology. In fact, I would term this as next generation technology. 2 centuries from now, when we've reinvented physics, electric propulsion, more aptly, is something like this. It's the analog of electric cars as they are to chemical or internal combustion cars. So just as we call these right now the cars that we typically drive around that use gas and combustion processes to ultimately push the vehicle around, there's a next generation technology that uses electricity or power to ultimately motivate or locomote the vehicle. In that same context, you can think of electric propulsion as the analog of electric cars. So the electric propulsion systems are the electric cars of space, and therefore we can think of it as the Nissan Leafs moving around the solar system. Okay, so it's a little less impressive, but ultimately it has significant advantages. And that ultimately stems from this point, which is that electric propulsion systems have low gas mileage for getting around space compared to traditional chemical rockets. So they are much more efficient at using fuel to get around space. And as a consequence, you can go further for less fuel and therefore less costs. So electric propulsion is the electric car of space. Okay, so now why ultimately does electric propulsion have this better gas mileage? And to look at that, we need to first compare it to what I like to call the enemy, the chemical rocket systems. Okay, so how do chemical rocket systems work? Well, first of all, they work quite well, and they've been around for a century now. But the central concept is this. You introduce a fuel and an oxidizer, in this case liquid hydrogen and liquid oxygen, into a combustion chamber. And then through a chemical reaction, the internal energy which exists in the bonds of those molecules is released, and is released in the form of heat. So it may not be showing up to you in the back, but these are small photon lines denoting heat being released. Now ultimately that heat is converted into increasing the temperature of the propellant, and that temperature, randomized thermal energy, is directed into directed kinetic energy, which is the downstream side of the nozzle right there, leading to a net thrust of the system in the opposite direction. Now the key point here, and again these are the only 2 equations I'll show today, I do promise, is this right here. The specific impulse, which is a proxy for how fast the propellant is coming out, so the exhaust speed. The specific impulse for this system depends directly on the energy that is stored in the bonds of those molecules. Okay. Which means that, in principle, if you can find molecules that have lots of energy stored into them, you can make the exhaust of the propellant go out much more quickly. But we are limited by nature. There are only certain chemical bonds that we know of which have a large amount of energy, and indeed that ultimately puts a cap on how fast we can send the propellant out the back. So chemical systems right now, the fastest that propellant goes out the back right now is about 4.5 kilometers per second, which corresponds to a specific impulse of about 450 seconds. Okay, so there's a chemical system spewing things out the back at about 4.5 kilometers a second. Now let's contrast that with electric propulsion. The key innovation for electric propulsion is that you decouple the mechanism for adding energy to the propellant from the propellant itself. So instead of using chemical energy and internal chemical bonds to ultimately heat up the propellant, electric propulsion systems use an external power supply to add energy to the propellant. In this case, it would be something like solar panels. So solar panels go through a power processing unit and ultimately energize the propellant. In this case, I'm showing a classic Hall effect thruster, which is operating on the gas of choice that we use, which is xenon. So that power from the power supply is converted into ultimately accelerating the propellant out the back. And the ultimate consequence of this is that the specific impulse, or exhaust velocity, now depends on the power supply, or P, how much power you're putting into the system. So the key takeaway from this is that as opposed to chemical systems where you're limited by nature, how much internal chemical energy is stored in the bonds, with electric propulsion systems, in principle, if you build a bigger power supply, you can make the propellant come out as fast as you want it to. Okay. So why is that an advantage, contrasting these 2? Well, it all comes down to conservation of momentum. How do rockets get around into space? They throw things out the back. Okay. So you can throw things out the back in 2 ways. You can throw a lot of stuff out the back at very slow speed and get a momentum transfer, which is the chemical rocket way, or you can send a little bit out the back at very high speeds, which is the electric propulsion way. The ultimate takeaway from this is mass times velocity. They both ultimately give the same impulse to the rocket, but one requires significantly less fuel because you're sending out the back much more quickly. And as a consequence, we can see just from this kind of cartoon picture that electric thruster systems require less propellant to accomplish a given maneuver in space. And that's why there's so-called better gas mileage for moving around space. Now, the implications of this directly translate to cost. And you can see a direct comparison between these two. If I were to use a satellite in space with a traditional chemical propulsion system, that's what's shown on the left, if I wanted to move that satellite to a different orbit, I would have to have propellant tanks notionally shown as that size. However, if I switch over to an electric propulsion system, the propellant tank requirements would be significantly reduced. And in fact, you can show it's about a factor of 10 smaller, which means that ultimately in most of these systems, the payload is dominated by how much propellant you need to move around the space. That translates to a factor of 10 reduction in the mass launch requirements, and therefore a factor of 10 reduction in the cost requirements for getting these things to space. So ultimately, the payload that is launched on top of chemical systems into orbit is significantly lower. I'll caveat this here, which is that electric propulsion systems can never generate enough thrust to get off the surface of the Earth. Okay. So you can never use an electric propulsion system to actually launch from Cape Canaveral. These things only work in space, and there are reasons for that, but ultimately the takeaway is that if you wanted to launch even a small payload off the surface of the Earth using electric propulsion systems, you need several gigawatts of power. And of course, that would be multiple power systems that are currently powering Detroit, for example. So too much mass to do that. Okay, so the takeaway from this is that when we do launch payloads, we can start to do interesting things like this. So here I'm showing on the left-hand side two standard payloads that have been launched by Boeing. These are both commercial systems which provide, in this case, communications to the Earth at geostationary orbit. So they're both intended for things like satellite TV. Now, typically, if you used a chemical propulsion system to reorient the orbit of these devices, they'd have to be launched separately. So they require two separate launches, both accruing a commensurate cost. But if you use electric propulsion systems on board, you can start to do interesting things like this, where you stack them on top of each other. And now they can be launched together. Once they're launched in space, they turn on their electric rockets and move to their new orbits with significantly less required payload. Okay. So from a commercial perspective, electric propulsion is an extremely attractive technology, and indeed industry projections suggest that in the next 10 years, about 80% of launches will be using electric propulsion from a commercial perspective. Okay. It also has implications for the exploration of space. And in fact, electric propulsion has already flown. So what I'm showing right here is the Dawn exploration mission. So Dawn was the first scientific mission to ever orbit two bodies outside of the Earth-Moon mission. It went to Vesta first, and then it went to Ceres, two near-Earth asteroids in the asteroid belt. And it was able to do it with a propellant tank which is about the size of a small Volkswagen. Okay. So ultimately, it was able to putt around the space with an extremely small gas tank, and that was entirely enabled by electric propulsion. Indeed, you could show that with traditional chemical onboard propulsion systems, this type of mission would not be possible. So electric propulsion is considered enabling technology not only from the commercial perspective, but also from the space exploration perspective. In fact, Dawn is actually in the last stages of its operation right now, and is still orbiting Ceres, moving to a different orbit for doing scientific investigation. Now, that being said, electric propulsion is not only for robotic exploration, which is the Dawn system, but it can also be used for crewed exploration in principle, and that's the idea where the X3 system comes in. And I'll talk about what the advantages right there. So why this technology? Well, the first is it's electric propulsion, and the key takeaway from this is that electric propulsion systems have better gas mileage and therefore save in terms of cost when you want to go around exploring the system. So EP allows you to do effectively more for less. Now, the X3 system, which we're considering for crewed exploration, and I'll return to the justification for that in just a couple charts, is that the X3 leverages what's so-called a mature technology. It's the Hall effect thruster, and it does it in a clever way such that we might be able to scale up to the powers that are required for crewed exploration. So what is this Hall effect thruster, and why in particular are we looking at it for the X3 system? Now, there are many different ways to convert external power supplies, solar arrays, into directed exhaust, and this is what I like to call the pantheon of electric propulsion. All these different concepts have been flown to space, with the exception of the advanced concepts on the very far right-hand side. So depending on the power that's available to you in space, for example, with solar panels, or in some cases, limited cases, nuclear power, you can use different types of electric propulsion systems to move around. Now, of all of these, the ion engine and the Hall effect thruster are what's considered the most mature of the technologies. That is, they have several flight missions where they've demonstrated performance and achieved their mission goals. And specifically, Hall effect thrusters is quickly emerging as the dominant technology considered in the field. In fact, of most commercial launches that are currently done right now, the Hall effect thruster is the system of choice for moving those commercial systems around, and it's been baseline for a number of different deep space exploration missions coming up in the next 5 to 10 years. So Hall effect thruster, let me just say a couple words about this. This technology has actually been around since the 1970s. Depending on who you talk to, is either first proposed in the U.S. or the Soviet Union. But without exception, unambiguously, I'll say that the Soviet Union were the first to demonstrate and use it in flight, which is in the 1970s. So the Hall effect thruster is an interesting story related to it. The electric propulsion community went down two different paths, returning to this chart again. So the Americans elected to use ion engines, and they developed this technology and flew them on some demonstration technologies missions in the 60s, 70s, and 80s, whereas the Soviet Union went down the parallel path of using Hall effect thrusters. At that point, the Hall effect thruster largely had been dismissed by Americans because they didn't think the performance could be sufficiently high to achieve the mission objectives they wanted to. Now, come around 1991, when the Iron Curtain is falling, the Soviet Union is finally able to publish their papers in public. And the American scientists see some of these, and they can't believe the performance measurements that they're seeing for the Hall effect thruster. So the Soviet Union, or now Russia, invites them over and says, well, if you don't believe it, test it yourself. So they go over and they test the Hall effect thruster, and they say, these things are incredible, and we better start using them. So 10 years later, the United States starts flying these things commercially, and Space Systems Loral flew the first Hall effect thruster on a commercial payload, though it was a Russian-built thruster. The first domestically built thruster was the BPT-4000, or called the XR-5 in 2011. And now Hall effect thrusters have reached a level of maturity where they are continuously being baselined by NASA for deep space exploration missions. Indeed, as I'll mention later, the X3 is a next generation iteration of the Hall effect thruster. So here are a couple of different key features of these devices in contrast to other technologies. The first one is that they have so-called moderate thrust density, which means that you can get a lot of thrust for a smaller package, okay, in contrast to other technologies. They have high specific impulse. Remember, that corresponds to exhaust velocity. So the higher exhaust velocity, the better fuel economy your system has. Hall effect thrusters have pretty good fuel economy. And the last one is electrical efficiency. Well, I didn't touch on this one before, but whenever you have a power supply, not all of that power gets converted into the load. And for Hall effect thrusters, about 60% of that is converted. It turns out in the electric propulsion pantheon, that's a pretty good conversion efficiency. Ion thrusters are the only better one, and they're about 70 to 80%. So Hall effect thrusters have pretty good power conversion efficiencies. Now, since this is such a pivotal component of the X3 system, I do want to say a couple words about how these devices work. I'm going to talk a little bit about particle trajectories and electric and magnetic fields and how they relate to the operation of these devices, but we'll step bit by bit through the individual components of the operation of this device. So what I'm showing up here is a Hall effect thruster which is firing in a vacuum test facility. That's on the right-hand side. And you can see the propellant which is being expelled downstream. Remember, it's coming out very fast. So Hall effect thrusters, specific impulse about 2,000 seconds, which means an exhaust velocity of 20 kilometers a second. Remember, chemical rockets are 4.5 kilometers a second, so we're about 5 times faster. Okay. So that's propelling propellant downstream, and then I'm showing a 3/4 view of a Hall effect schematic on the left-hand side. There are a couple different key elements I want to draw your attention to, and we'll talk about them in different measure. Hall effect thrusters are annular devices, which means they are axisymmetric, a cylindrical geometry, and the discharge is located in that kind of cylindrical tube which is rotated around the axis of symmetry. So you can kind of think of it like a fluorescent light bulb which has been turned into a donut. Okay? And in fact, many of the similar processes occur in both devices. The Hall effect thruster is characterized by very strong magnetic fields. Magnetic fields are applied across that annulus, and you can see those denoted by the black lines next to that big B. And a strong electric field is applied across that magnetic field. The electric field is created by the power supply, in this case, solar arrays. Okay. So let's talk about the different steps about how these devices work. Well, the first step is we use a thermionically emitting cathode to generate electrons. So electrons are emitted from the cathode surface, and they go into free space. Okay. We then connect that cathode to a power supply. So again, for reference, we have a 3/4 view on the right-hand side. On the left-hand side, I'm just showing a pure cross-section of the Hall effect thruster. So we create an electric field using this power supply linking an anode upstream electrode to the cathode electrode downstream. And of course, electrons being free charge carriers will want to follow that electric field. So those electrons flow into the annulus of the device. And right now we've created a very low resistance discharge. So electrons are just flowing. Now so far this isn't a very good thruster. Okay, all we're doing is dissipating heat through the resistive elements. So the next step is to somehow impede that electron motion. Because we don't want electrons ultimately to just complete the circuit, we want electrons to hang around a little bit to do some interesting things, ultimately related to the acceleration of the propellant. In this case, we apply a very strong magnetic field, as mentioned before, across the annular discharge channel of these devices. That's denoted by the yellow lines. This strong electric field serves to trap the electrons. And this is an axiomatic truth about charged particles, in particular electrons. If you have a strong enough magnetic field, electrons will be tied to it. So it serves as an effective impedance barrier, preventing those electrons from transiting. And indeed, when you have a strong electric field applied in the axial direction, cross of that magnetic field, those electrons aren't just going to be trapped on that surface, they're going to be rotating around the axis of symmetry. And you can see that on the right-hand side right here. So that kind of spiral trajectory is what the actual motion of each individual electron looks like as they go around these devices. Those electrons zip around at very, very high speeds, actually about 100 kilometers a second. Which leads to a very strong current in the azimuthal direction of these devices, which is called the Hall effect current, which is where these devices derive their name. So they're Hall effect thrusters, which are host to very strong Hall effect currents. Okay, now as these electrons zip around at a very high speed, so still it's not a very good thruster. So the next step is to introduce a heavier species. And in particular, in this case, I'm showing xenon. So it didn't show up right here, but there are little XEs in each of those little purple dots. So xenon right now is introduced as a neutral gas, and it is flowed through the anode. As those neutrals transit down the thrusters, just diffusing their way through there, they have to run the gauntlet of these very strongly rotating electrons. And as those electrons rotate, they will impact some of those neutrals as they transit. And there's sufficient energy that those electrons will knock additional electrons off of those neutral particles. And that creates positive particles. Now we have a soup of electrons and ions. But if you were to integrate all the charge, it'd ultimately still be neutral. But this soup of ions and electrons is called a plasma. So we've created a plasma by having these electrons impact the neutrals. Now, this is an exciting and advantageous thing to do because now we have this heavier species which we can accelerate with the electric field. And the key point to take away from this is that even though ions in principle are also charged particles and susceptible to magnetic fields, they're much heavier. And if you tailor your magnetic field in the right way, you can trap the electrons, but the ions won't feel the magnetic field. So there's kind of a balance to be struck right there. And if the ions don't feel the magnetic field, the only force they feel is the electric field we originally applied. That electric field accelerates those ions downstream and does it at a very high velocity, 20 kilometers a second. So electrons are stuck in their trajectories, going around in that buzzsaw Hall effect drift, and the ions are accelerated downstream. Now, the ions ultimately are positive particles. And if we were to leave things as they were, ultimately we'd be ejecting positive net particle from the device, which would mean the Hall thruster itself would be charged negatively. That could lead to a cloud downstream of positive particles and an electrically negative thruster. So ultimately, those positive particles would be attracted back to the thruster, and that would totally nullify your thrust. So the cathode serves a dual purpose, which is to allow additional electrons to go downstream, and they neutralize the exhaust. So even though this all relies on creating positive and negative particles and manipulating different trajectories, if you go far enough away from a thruster, the propellant is ultimately neutralized, so it just returns to being xenon. Okay. So Hall effect thrusters. Now that's the mechanism for how they work, and it has those different advantages as I mentioned before. But the key takeaways from this are, number one, they're actually pretty simple to build. Graduate students can do it and make them work relatively well within 1 or 2 years of their PhD work. They turn out to be robust. It's pretty hard to break them. And through 20 or 30 years of iteration, we've ultimately optimized the operation of these devices. So they're pretty good at turning external power into directed exhaust. We have relative confidence in their stability and operation on orbit. In fact, a key bragging point about these devices are twofold. Number one is one has never failed on orbit from a mission operation perspective, and two, in some cases, they've actually saved missions which were originally relying on chemical rockets to do their boosting, which failed, and the electric propulsion system had to come in and save the day. Okay, so bragging points for this electric propulsion technology. And this last one is, again, the 60% efficiency and very high exhaust velocity, so very good fuel economy. So Hall effect thrusters, if I want you to take away two things from this, number one is that they're a form of electric propulsion, have very good fuel economy, okay, for moving around space. And number two, this is a very proven technology and therefore very advantageous for the exploration of space. So the X3, I'll say, leverages this technology. Okay. The X3 itself is not a traditional Hall effect thruster, but it is based on the concept. Okay. And it's based on the concept in the following way. On the left-hand side, I'm showing the traditional Hall effect thruster to scale that we operate in our laboratory. And these are the types of devices that are currently flown in space on commercial systems. That's a traditional Hall effect thruster. And of course, on the right-hand side, I'm showing the X3 engine. So a 3-channel configuration. And of course, what immediately pops out to you is that the Hall effect thruster has 1 annular discharge and the X3 system has 3 annular discharge. Of course, it's much bigger as well. The X3 is about a meter in diameter, 80 centimeters, and weighs about 200 kilograms. So it's a significantly bigger device. The question that begs is, why do we do this channel nesting? Okay? So why do we go from a Hall effect thruster, which we've already demonstrated hundreds of times on orbit, and why are we exploring this technology which uses 3 effectively Hall effect thrusters stacked up concentrically? Okay, and the answer ultimately comes down to this point, which is that electric propulsion systems are very low thrust devices. Okay. I mentioned this before, we can never use Hall effect thrusters to launch off the surface of the Earth. And in fact, that's an extreme case. Hall effect thrusters and electric propulsion systems in general are extremely low thrust, and they generate very low acceleration for any craft that they're attached to. In fact, a good way to illustrate this is that if I were to try to dangle something in the plume of the thruster and see if it could support it just from the force that's emitted from it, the most I could do is a small sheet of paper. Okay, you can see I borrowed this from another talk I gave, which was to a plasma audience, and that's a well-known book in our community, which is very tiny and are all plasma formulae. So effectively, this is a measure of how much force these devices generate. To give you quantitative numbers, it's about 300 millinewtons. So Hall effect thrusters would never be able to launch something off the surface of the Earth, and in fact, they accelerate things very slowly because they generate very low thrust. Okay, low thrust equals low acceleration. What this ultimately means is that Hall effect thrusters, though they have very good fuel economy, ultimately require a lot of time in order to move things around in space. Because they have very low acceleration, if you ever want to get up to a given velocity, you have to leave the thruster on continuously for weeks, months, and in many cases for years. Okay, so they're like the little engines in code of space. They have very good fuel economy, but take a very long time to accelerate. Okay. So to give some context to that, I'm going to show the 3 examples I showed before. On the left-hand side, we have the commercial system, which is used by Boeing. On the upper right-hand side, we have the robotic exploration mission that was launched by NASA using the ion thruster, and then we have these next generation missions which are considered for the journey to Mars. And to give you a sense for the timelines required for each of these missions, if you're to use traditional electric propulsion systems, here are the numbers. Okay. So to boost from a low Earth orbit to a geo orbit for that satellite system would take about 3 months. Okay. For the Dawn mission, it was actually launched about 8 years ago, so it took 7 years to reach its different destinations. So long time of continuous thrusting. And then for the journey to Mars, if you were to use kind of traditional Hall effect thrusters, it could take 2 to 5 years, which is prohibitively long for any kind of astronaut to be exposed to the vacuum of space. Okay. So the ultimate takeaway from this is that if you want to do these types of missions with electric propulsion systems as they currently exist, these 5 to 10 kilowatt systems, while it's attractive for both commercial systems where there are no people on board and both robotic missions where there are no people on board, the time durations become prohibitively large for these deep exploration missions. Okay. So to put some context to that, and I want to show a graph right here, which shows how we can ultimately overcome this issue for we use an electric propulsion system. Okay, so this is from a simple mission study that I did, looking at if I want to send 75 megatons. Okay, that's kind of what is anticipated to be the necessary payload to support a human presence on Mars for a couple of months, from a low Earth orbit. So it's been launched up by a commercial rocket system to Mars and using a propulsion system that has that specific impulse of 1800 seconds. So again, remember that's a proxy for fuel economy. On the left-hand axis, I'm going to show the transit time, how long it takes that system to get to Mars. And on the bottom axis, I'm going to show how much power is actually delivered to the system. So for some context, commercial systems in space use solar panels, and they operate at about 5 kilowatts. Okay. Transit time here is on the left-hand. So this is a reasonable transit time for crewed missions. It doesn't show up in good contrast here, but up to about 1 year, there's a blue rectangle, denoting kind of the anticipated or expected amount of time that astronauts could reasonably get to Mars and still be in good health, so about 1 year. And then I'm going to show a trend which shows the trade between transit time and power. Okay. The ultimate takeaway from this chart is that as we increase thruster power, electric propulsion power, the required transit time decreases. So if we look at the highest power Hall thrusters that have been flown to date, which operated about 5 kilowatts, we can see that the required time to get to Mars for this context would be about 100 years. Okay. Now the trade-off is that it wouldn't require much fuel, right? So you'd save a lot of money, but your astronauts would end up there as skeletons. Okay. Well, it depends on what the environment is of the space vehicle, right? So I don't know. It depends on the trade you want to do there, but ultimately the takeaway is that current technology is not going to cut it if we want to do it in what we're calling a reasonable amount of time. Okay. Now, the highest power Hall thruster that is being currently considered by NASA and has been baseline for missions upcoming in the next 5 years only scales to 12.5 kilowatts. Okay. So that does give us some trade in terms of time. Now it's only going to take 20 years, but still that's prohibitively long. People would almost undoubtedly die of cancer or starvation on the way there. Okay. So the ultimate question here is how can we generate electric propulsion systems that still allow us to leverage the good fuel economy while at the same time allowing us to operate at higher powers in such a way that we have higher thrust and therefore lower transit times. So the trade-off here is that if we increase the power of the system, it requires less time to get to the destination, and therefore we can start to enter the realm of possibility of using electric propulsion for crewed exploration while still reaping the benefits of having good fuel economy. Okay, so to contrast that here, we have the Hall effect thruster on the left-hand side, and the question we're asking is how can we leverage or scale this technology in such a way that we can get to the 100 kilowatt level where we can have reasonable transit times to Mars and potentially beyond. So the left-hand Hall effect thruster found on the left-hand side, and the right-hand is one potential strategy for making these systems larger. Okay. Now, Hall effect thrusters, I mentioned before, we've established some well-known empirical scaling laws for how to build these devices. We can do it quite effectively. And the implication is that we also know how to scale them up in power if we want to leverage these current scaling laws. So if we want to use this so-called single channel configuration and we want to generate one that's 100 or 200 kilowatt level power level to facilitate these deep or fast transit to Mars, we have to generate something that looks like this. So I'm showing actually not to scale. The diameter of this system on the right-hand side would be about 1.5 to 2 meters. So it's a very large system. But in principle, we could do this. We could scale the technology using known scaling laws to get to higher powers. The trade-off is, of course, surface area. Now, an alternative which might lend itself to make higher power systems effectively for getting to interplanetary destinations is just to take this one thruster and to copy it. So why not just build an array of 16 of these devices? Okay. That seems like an elegant solution in some sense because we already know that the one thruster operates quite well. So why not put 16 of them back to back to back and therefore have an array which is immediately ready to turn on? Yeah, poor packing factor is definitely one. The other one is complexity. It's a trade-off, right? So if you have 16 of these devices operating concurrently, how do you ultimately guarantee that you can facilitate flow in a way that won't lead to failures in the power systems? So what's not really shown here is that 16 systems require 16 different power processing systems and 16 different flow systems. Yeah. Sure, yeah, thrust balance as well. You can gimbal these and you can vary thrust a little bit, but you're right, that's an interesting trade that you'd have to look at. So the complexity and these other issues that you're inviting are significant challenges with this kind of array of this technology. That being said, people have looked at trying to do these arrays for deep space exploration. So the X3 actually marries these two concepts, and as I alluded to before, instead of using just one large annular device or using 16 smaller ones, it stacks them in a geometrically efficient way. Okay? The most efficient way to stack devices is in a spherical or a circular pattern in 2D, and in fact that's what the X3 does. So effectively what you can think of for the X3 is that it's 3 Hall effect thrusters with increasing diameter which are stacked concentrically. So it's a very efficient use of geometry, while at the same time, this is an important point, leveraging many of the known design scaling laws that have gone into traditional Hall effect thrusters. So the ultimate takeaway from this is that you can contrast these two side to side. You have on the left-hand side that larger device I was mentioning, which can operate at 200 kilowatts. That's using known scaling laws to make these larger devices. And the right-hand side, you have a nested Hall thruster. So 3 of these channels stacked concentrically. And the ultimate takeaway from this is the amount of mass required for kilowatt for the devices is significantly lower if you move to a nested channel configuration. So when we talk about space, mass is one of the major drivers. And so the implication of this is that by using a nested channel Hall thruster technology, you can save on this critical parameter. In fact, we've done some parametric trait studies looking at things, contrasting not only single configurations with the nested configurations, but we've also looked at looking at these arrays. So the third option I showed, which is stacking 16. The ultimate takeaway is the X3 does seem to be the optimal configuration comparing these three different technologies for trying to scale up Hall effect thrusters to these higher powers. Okay, so what is the ultimate takeaway from this, from the implication of thrust? On the left-hand side, we have this Hall effect thruster at 6 kilowatts, which is able to support a small sheet of paper, and now we move to the X3, which is able to support a small book. Okay, so the increases in thrust are profound. That is to say, we would never use the X3 to launch again off the surface of the Earth, but effectively we've been able to increase the thrust by over a factor of 10. Okay? And therefore, if we use the X3 system, now it starts to become more plausible to reach deep space exploration destinations like Mars, okay, with this technology. Okay, and in fact, trade studies have shown that once you start to scale these technologies to the 200 or 300 kilowatt level, it starts to become possible to reach different destinations. So a little bit lower hanging fruit is to not land on Mars, but to go on the significantly less steep gradient well of Phobos, one of the Mars moons. On the right-hand side, if you have 600 kilowatts, which is not that far of a jump from 100 or 200 kilowatt demonstration, you could actually start to send people to Mars. Okay. So ultimately, the two advantages for the X3 technology, and why we're excited about it from NASA's perspective, again, are that it's a type of electric propulsion, so very good fuel economy, and number two is that it leverages or uses a mature technology but does it in a novel way, so that we can use technology that we know works but scale up to higher powers. Okay, so that's why the X3 is a winning technology from our perspective from NASA, for NASA. Okay, so with that said, hopefully I've motivated to you why we're looking at this technology, and now I want to talk a little bit about the technology development that we've been doing with our partners here, Aerojet Rocketdyne, NASA, and then ultimately the work that we've done at the University of Michigan. Okay, so here are a couple of the design specifications of the X3 system as it exists, and on the left-hand side you can see one of the graduate students working on it. This has actually made its way onto the internet. It's been in a couple of different articles. That's now Dr. Scott Hall, who is an employee at NASA Glenn, so he works on the X3 from the other side. But you can see a couple of the design specifications here, diameter, specific impulse, and as I mentioned before, the gas that we like to use for these devices is xenon. Okay. Here's a little bit of the development history of the X3 system. We started off, again, from a single channel configuration, and we progressively worked our way to this, what we perceived to be an optimized geometric configuration of the device. So the X3 actually borrows heritage from a decades-long research program that was initiated at NASA, looking at ways that we can improve the performance of Hall effect thrusters at the kind of target performance metrics required for deep space exploration. So how do we scale the power of these devices? How do we improve the efficiency? How do we ultimately increase the specific impulse? Okay, so one of the things that came out of this is this idea that we should start to use concentrically stacked thrusters. Michigan isn't the only one to have done this. There's a commercial company as well that has looked at stacking thrusters, though we've taken it to the next power level. And in fact, 2009, it formed the basis of a dissertation which was ultimately geared toward answering the question, can you in fact even stack this technology in such a way that the thruster will turn on and operate? And ultimately the answer to that thesis was yes, but the thruster did not work quite as well as they were hoping. So they used some of those lessons learned, and they went from 1 to 2 to 3 channel thrusters, and that's what's shown on the lower plot right here. So in 2009, there was motivation not only from NASA but from the Air Force to build a prototype demonstration system of a 3-channel nested Hall thruster, and that's what's shown here. So the X3 actually was conceived back in 2009, predating the NASA program. And in fact, in 2013, the system was first turned on at 30% of its design power, so 30 kilowatts. Now you might ask why we didn't actually ramp it up to 100 kilowatts to begin with, and the answer is that it broke our facility. It was so powerful, and I'll talk a little bit about that in a second. But it's a fun problem to have, that when your technology is getting too powerful for your test diagnostics. Okay. Now, 2013, 2015, that was Dr. Scott Hall's thesis work, where they really focused on doing design iteration to improve the performance, and we got to the point where it was sufficiently competitive that we could propose it to NASA in conjunction with our partners of Aerojet Rocketdyne. and NASA Glenn Research Center and the NASA Jet Propulsion Laboratory. Okay, so on the Next Step program, there are a couple different objectives that have kind of oriented and guided the technology development program that we've engaged in the past 2.5 years at this point. So I've listed these, and I'm going to talk about them in different measure and kind of the challenges they represent. So the Next Step program, the idea was to take a technology which exists at TRL 2 or TRL 3. For those that aren't familiar, TRL means technology readiness level. So TRL 1 is a technology which you have an idea and you've scribbled it down on a cocktail napkin, okay, and you think it'll work. TRL 9 is something that's been flown and demonstrated in space multiple times for actual mission operations. So when we say TRL 2 or TRL 3, we mean it's been demonstrated usually in the laboratory with some components which actually been operated. The goal of this program was to demonstrate this technology at TRL 5. That means that not only has the thruster been built, but we have power supplies that work with it and a flow system that's integrated. And it's all been demonstrated in a vacuum environment. Okay. So the goal of this was to take the 3 different technologies that were identified and to develop them to a TRL level 5 readiness level, and then ultimately to operate them for 100 hours continuously. So again, mentioning before, if we want to get to deep space exploration missions, or destinations, excuse me, we need to run these devices continuously. And for a Mars exploration mission, that'd mean running this thruster continuously for 6 months. So 100 hours is several orders of magnitude lower than that requirement. But for this demonstration purposes, they say, well, 100 hours would be sufficient to demonstrate that the technology operates at steady state, and therefore we have sufficient interest to continue forward funding. Okay, so those are the requirements of the program to be demonstrated by year 3. The objectives here are looking further down in the future, and these all relate to kind of mission requirements. I'll return to the most significant and glaring of these, as I mentioned before, and that's they ultimately want to be able to demonstrate the lifetime of these devices for 10,000 hours. Okay, so this is the beginning of the Next Step program, and I just want to kind of briefly step through the different steps that we've taken, and I'll show a couple images of the thruster operating. But at 2016, the program kicks off, and we've done quite a bit of work in the past 2 years in trying to understand not only the operation of this device from a practical perspective, from a fundamental perspective. So that's led ultimately to some design iterations, both in how we implement the magnetic field in these devices as well as the electric field configurations. Ultimately, those implementations and improvements were demonstrated in a test done at NASA Glenn Research Center. And in fact, we demonstrated the thruster up to its design power requirements for this mission, or for this program, which is 100 kilowatts. Starting in 2018, we've moved the thruster back to the University of Michigan, where we have our own test facilities to do some low-level power integration testing. And then in just this past month, we've done additional testing at the University of Michigan to prove out some additional iterations of the technology, all in anticipation of this test, which is planned for October or November. Just a little bit of schedule push, where we'll run the thruster for 100 hours continuously back in NASA Glenn Research Center. Okay, so I want to talk a little bit about the results here. Beginning first with the demonstrations that were done in 2017 in August at the Glenn Research Center with Scott's thesis work. So for this demonstration test, we operated the thruster in many different configurations. And kind of one of the interesting and attractive features of the X3 system, which I didn't touch upon, is that not only can it scale to very high powers, but it can scale to very low powers too. And that can be accomplished just by turning channels on and off interchangeably. So this device can operate with just the cursor does work with the inner one, or it could operate with the middle one or the outer one. All 3 firing together are different combinations, and that's what you can see on the right-hand side. So for this demonstration test, they actually operated the thruster at 47 different operating conditions to look at performance. This is what the ultimate results show on the right-hand side. Thrust is the left-hand axis, and discharge power is on the bottom axis. So thrust, it's sometimes hard to convert these SI units into intuitive metrics. So a thrust of 5 newtons corresponds to a weight of about 1 pound. Okay, so that's that book that it's supporting, as Plume mentioned before. And what we can see here is that in this demonstration test, the throttling capability, the ability of the thruster to go from low power to high power, was demonstrated at a couple different operating conditions. And ultimately, the highest power and highest thrust that was demonstrated is right up here, which is, they showed 5.4 newtons, so about a pound of thrust. These are just operating conditions, 400 volts, and then ultimately at the required power of 100 kilowatts. So from the programmatic level, this is kind of the first demonstration of the highest power required for this for the next step. Here we are all the way back down here. This is where thrusters are actually operating on orbit. So we've done a 2 order of magnitude increase in demonstrated power. So the X3 system is working well, and it's nice you get a shout out, or Scott got a shout out from space.com, which says the ion thruster prototype breaks records in tests. There are a couple different things wrong with this headline. Number one, it's not an ion thruster, it's a Hall thruster. That's a common thing in the media. And number two, ion thrusters have been demonstrated at 500 kilowatts before. So it's the highest power demonstration of a Hall effect thruster, and we'll leave it at that. Okay, so there's a little bit of fake news there, but it was in good spirit. Okay. So returning here, the ultimate takeaway from this is that the Hall effect thruster for the XR program in 2017 had been demonstrated the requirements. Now I do want to touch a little bit on the work that we've been doing at the University of Michigan just in the past 6 months. First from a low power systems level test, and then also from a risk mitigation test. So for the systems level test, and this is more for the technology people in the audience, the thruster itself is just one small component of the actual system, and it turns out that the other parts of it can be more difficult to implement. So how do you convert power from solar arrays into power that the thruster can actually operate on? And then how do you transfer gas from their storage containers, high pressure xenon containers, to actually flowing in the thruster itself at relatively low flow rates. So we're talking about a couple milligrams per second. Okay. So these are both interesting challenges, and they need to be integrated with controllers in such a way that you can guarantee that when the operator on Earth pushes the button to run the thruster, that you get to the required power level and that you operate stably there for years. Okay. So one of the goals of the XR 100 program was to demonstrate the integration of the thruster with these different system levels. And before you can fly, you need to walk. So we did a reduced power demonstration test at University of Michigan, where Aerojet Rocketdyne brought out all of their technology, and we integrated with the thruster and showed that they do in fact work together. Now moving into July, there were some actually interesting challenges from the thruster perspective that emerged from this testing in 2018, specifically with respect to increasing the ability of this thruster to push propellant out at even higher and higher speeds required for the program. So there were a couple design modifications that were required and implemented, and so we had a month and a half long campaign starting in June to prove those out. So now I'm going to show a picture of the thruster actually firing from that campaign. If I can, there we go. Okay, this is about 15 minutes long, so I'm just going to take a quick bathroom break and I'll be back. I'm just kidding, it's a long time to just watch this thing move over and over again, okay? It's just firing at a steady state. You can see some slight fluctuations in luminosity, but I do want to show the ability to scale this device. So here we go. We went with one inner channel operating, so this is all 3 channels firing concurrently, and they're sending xenon downstream. Okay. A couple different elements here to point out. This is a cathode, which is providing the electrons. Those electrons are streaming from that source into these different channels, and we just turned off the inner channel. So now the thruster is operating on these 2 middle and outer channels. Okay, again, all the xenon is firing. Some of these kind of high frequency flashes you're seeing, they're just artifacts of the video frame rate. Okay. And then a couple minutes later on, we turn on the middle channel again. Okay, so we soft start this, and now we've increased the effective thrust of this device. So this is all operating in a vacuum test facility. We've evacuated to approximate space, and it's all firing downstream. Now at this condition, we were operating about 40 kilowatts, and all that's being collected downstream by our chamber and heating up quite significantly to the point that we actually can touch the end bell. So that's a demonstration of the thruster operating. Here's kind of the takeaway chart from the work that we've been doing to date, which is we've been combining modeling efforts, largely led by the Jet Propulsion Laboratory, with our own testing work and design modifications. And this is the state of the program right now, which is we're now, we think, confident moving into this year 3 test where we'll do the 100-hour demonstration, and then hopefully looking beyond to actually spacecraft integration, maybe 10 or 20 years down the line. So ultimately we're on track for TRL-5. Okay, so that's talking about the work that we've done. We've talked about the motivation, and I just want to say a couple words about the ongoing challenges with demonstrating these systems. Looking beyond just the program right now, which will end in October, to ultimately putting these things on a spacecraft to support crewed exploration. Okay, so I'm going to throw the requirements back up here, and again, we've hit the 100 kilowatt requirement, and we're going to try to hit the 100-hour requirement in October. But looking to the future, the most notable challenge is this one right here. Okay, so how do we go from a 100-hour demonstration to test facility to a 10,000-hour demonstration test facility? And this is actually a challenge which is not unique to the X3 thruster. It occurs across the field of electric propulsion, which is these devices need to operate continuously for years in some cases. How do you ultimately prove that something will work autonomously in space for multiple years of operation? Okay. And to put that in context, I challenge you to think of a piece of equipment that exists on Earth that doesn't require maintenance on a relatively regular schedule. Now imagine taking your refrigerator and putting it in space and being confident it'll operate 5 years from now after being exposed to radiation, okay, and continuous erosion and bombardment. Okay. And in fact, what we find for these thrusters is that when they start off with this pristine annular discharge chamber at the beginning of life, if you run them for 10,000 hours in this case, this is a smaller configuration device, you will erode that away. And in fact, in some cases, you can erode enough material away that the thruster will fail. Okay. So these are significant life-limiting challenges with these devices. And the challenge from the perspective of a systems level flight requirements is how do you demonstrate the lifetime of these systems? Okay. So how do we go about that? Well, the traditional technique is to do direct life testing. And this is as simple as it sounds. You take a thruster, you get a facility, you put the thruster in there, you run it, and you leave it for 5 years. And you come back and you see if it's still working. Okay. So create a space-like test environment in a vacuum test chamber. This is the large vacuum test facility at the University of Michigan. It's a 6 meter by 9 meter stainless steel tube, which we are capable of creating a vacuum-like environment in it. Okay. I'll actually make a quick shout out for the space enthusiasts in there. This is from the Apollo program. It was built in 1961, but now we use it for electric propulsion testing. Okay, number two is you run the thruster, and in fact, NASA's requirement right now is you have 50% margin. So if your mission is going to last for a year, you need to prove that the thruster will last for a year and a half. Okay. And then ultimately, you do an analysis of it. If the thruster does fail, you try to understand why, or if it doesn't fail, you try to prove that this test is sufficient to prove that the technology will last when it's operated in space. Okay. So I'll make this point. Direct life testing has been a very effective mechanism for proving out the lifetime of devices, particularly for low Earth applications, for geostationary birds, where the lifetime requirements are not as stringent. And it's actually been used for robotic missions as well. But we start to run into limitations for direct life testing, particularly for these high-power devices, when we move to higher throughputs in the facility. And I'll touch on those right now. So the first one is cost. Okay. The X3 system runs on xenon. Xenon exists in your headlights, among other things, which means that there's a pretty high demand for it. And in fact, that high demand far outstrips the requirements for electric propulsion. So xenon is not cheap. And if you wanted to run a demonstration mission where you use enough xenon to prove this device operating for 100 kilowatts for 1 year, the price tag would be about $15 million. Okay? And that's just to prove the thruster works. Okay? Number two is environment. Okay? First of all, even our best vacuum test facilities right now operate on thrusters that we know work in space and have been proven, so at the 4 or 5.5 kilowatt level. The pressure or density environment that we create in there is still about 5 orders of magnitude higher than actually exists in space. So we'll never be able to create the degree of vacuum that exists in space. And in fact, there are many different disparities that exist between a test facility and the space environment. Not just the background pressure, but probably the most obvious one is that there are walls. So in space, there are no walls, but vacuum test facilities have these large metallic containers. And it turns out that electric thrusters run off of electricity. So once you introduce these metallic barriers, you start to have current paths which would not exist in space. So that invites questions about the fidelity of ground testing versus on-orbit behavior. And the last one, of course, is poor statistics. So suppose that I do invest the $15 million, and I've proved to myself that this is a relatively representative environment, the space environment. I've invested my $15 million, I've invested the time of multiple laborers, and ultimately the test is run, and I've concluded it, and I've proved that the thruster operated without failure once. Okay. But of course, that's not very convincing to many people, and in particular, what you'd want to do is run this thruster and run this test multiple times, but now the time starts to add up, and there are only a couple test facilities in the world you could run this, so you can't do these things in parallel. So poor statistics, all right. That leaves the second option here, which is instead of doing direct life testing for these high-power devices, maybe we could do something which we call qualification through analysis, which is that if I have a sufficiently high-fidelity model for these devices, can I use that model to try to infer behavior? Okay. So the idea here is that we build the thruster. Okay, I'm going to return to the H9, the smaller hull thruster just for illustrative purposes here. And number two is that we build a high fidelity model of this. So maybe something in COMSOL, okay, that we code up and we validate against those experimental measurements. We then run the model for the mission duration. And in principle, we can do this at a much faster time scale than actually putting the thruster in a test facility. Okay. So we run the model to demonstrate a year-long mission, and we see how the thruster behaves in the simulated environment. Okay. And then we do that several thousand times. So this kind of answers the mail in all respects. It tells us whether or not the thruster fails, and allows us to generate things like these probability curves where we can see as a function of time whether or not the thruster will fail, identifying known failure modes. Okay. The advantage of this is that it's very cheap. It doesn't require the type of test facilities that I alluded to before or require any xenon. It just requires computational time. And indeed, NASA is starting to move toward this, suggesting that now you don't have to demonstrate 50% margin through direct life testing. If you could just demonstrate it in a test facility for 1 year, if you can demonstrate additional life through modeling, well, that should be just fine. Okay. The challenge with this, though, is that even though we use Hall effect thrusters and have done so for 40 years now, we don't have a sufficient understanding of how they work to be able to build high-fidelity models. Okay. So it's kind of an interesting point that I try to harp upon, which is that Hall thrusters work great, and they've been proven in multiple environments and different demonstrations, but they're actually fundamental physical processes that exist in these devices that we don't understand sufficiently, that we can actually program something like this up in COMSOL and be confident it'll predict behavior. Okay. So the major challenge right now, one of the major challenges in Hall effect thruster research is trying to demonstrate a sufficient understanding of the underlying physics that we can produce these high fidelity models, which would make our lives a lot easier for lifetime qualification. And in fact, that's one of the major challenges, not only for single channel Hall thrusters, but with extensibility to the 3-channel Hall thruster. It'd be great if we could have a high fidelity model which is able of predicting performance. And indeed, quite a bit of our research at the University of Michigan concentrates on this problem, which are some of the buzzwords that you heard in my introduction at the beginning, looking at things like microturbulence and RF interactions, trying to understand how they ultimately drive these poorly understood physics. Okay. I won't touch upon those, but suffice it to say, it's an open question that we're looking into. Okay. But don't get me wrong, Hall effect thrusters work great. Okay. It's just looking to this next generation demonstration of lifetime. Okay. The other challenge I want to touch on is just because it's kind of interesting, and which is that even though when you look at the video of these devices, it looks relatively steady state, if you look at them on a fast enough time scale, these are extremely dynamically rich environments. And there are lots of different types of oscillations that exist in these devices. They take on a different couple of flavors. So one is a so-called breathing mode oscillation, which is that if we were to look at this device at 20,000 frames per second, you'd see that it effectively looks like it turns on and off. Okay, it breathes. Now this is a universal phenomenon that exists in these devices, a so-called breathing mode oscillation. If you build a thruster, you know it will breathe, and you know about what frequency it will breathe. But to date, we actually don't understand necessarily why it happens. There are some models which show it's kind of a competition between neutral depletion and introduction of plasma, but these don't have what are so-called stability criteria. So we know it exists and we can predict the frequency, but we don't understand necessarily why it exists, or at least the energy that drives it. So you can see that from the video right here. The second one is called the so-called spoke mode, which is if you speed up your video here, you'll actually see these structures, some people call them gerbils, which kind of propagate around in the azimuthal direction. Formally, they're called the rotating spoke. We're not a very imaginative group. It's a spoke that looks like it rotates. Actually, this appears to play a role in how the thruster operates, but again, it's still kind of an open question. And then this last one is related to the electron source, which is the central point right here, the hollow cathode. And if you speed these things up, what you actually see is that they also breathe, but at a different frequency. So it's like the element is gasping. Now, ultimately, again, Hall thrusters work great, and they work in space, but they have all these sorts of interesting dynamical responses, which we don't quite understand, and we don't know how they play into an underlying understanding of the physics. So that's another significant leg of research that we do at the University of Michigan and the community at large. Okay, so from my perspective, these are kind of the fundamental physical challenges with direct applications to the qualification of the technology, but that ultimately goes to the question of what are the major challenges looking at the XR100 moving forward. This last one I'll just mention briefly here without putting a chart on it, which is a third alternative for demonstration. Just demonstrating life is not necessarily understanding the underlying physics, but maybe if you can design your thruster in such a way that you know it won't erode. And in fact, there have been significant inroads made at the NASA Jet Propulsion Laboratory as well as Aerojet Rocketdyne in part in parallel, that have demonstrated that you can make configurations where it effectively looks like the thruster does not erode over time. And the next step for this program, at least in my view, is to try to implement that technology for an X3 thruster. And in fact, one of our graduate students is looking at that right now, though on the 2-channel configuration. Again, if we run this thruster at 100 kilowatts in our facility right now in Michigan, it shuts down the facility. Though we have upgraded it just recently, and I'm confident in the next couple months we'll be able to run it full power. Okay. So yes, are there challenges? Many. Okay. So I'm going to wrap up here, hitting at the end of my hour. The first point I want you to take away is that we are looking toward the exploration of deep space, and we are looking toward crewed exploration of things like Mars, not just robotic. But if you're going to do things like that, you need innovative next-generation technology. And to address those 10 or 20-year horizon goals, NASA has invested in programs like the Next Step, where we're developing technologies, ultimately they could take us to these remote destinations. Okay, now to address the propulsion technology requirement for these deep space exploration missions, we feel that the X3 thruster, the 3-channel hull thruster, is a unique and an elegant solution to try to reach the power requirement levels for doing these deep space transits. And in particular, the X3 is good for 2 reasons. Number one, it is an electric propulsion system, and electric propulsion systems have great gas mileage. Okay, so cheaper costs. And number 2 is that it leverages a well-known and demonstrated technology, the Hall effect thruster, but does it in a unique and clever way. Okay. Now the XR100 system under the auspices of the Next Step program has been demonstrated, or will be demonstrated, hopefully by the end of the year, up to TRL level 5. And then it's just a hop, skip, and a jump, and a couple $100 million to get to a TRL level 9. So. Now there are some major challenges looking forward for this program, particularly for high power electric propulsion systems, not just the X3. Number 1 is how do you demonstrate the lifetime requirements, and number 2, and I'll say more broadly speaking, understanding the underlying physics sufficiently that you have confidence that the system will operate during its long transits to deep space and remote exploration missions. Okay. So the ultimate takeaway from this is that in large part our efforts at the University of Michigan, which is a research university, is to address many of these challenges and ultimately to use those to feed into the development of this technology. So with that, I do like to conclude with this slide, which is it takes a village to do any of this type of demonstration test, and I am woefully inadequate in the lab now that they have all these helpers who have far outstripped me, and you can see our research group here. So we have 12 graduate students and 1 postdoc, and there's the dean, Gallimore, and there's this guy who forgot to bring his polo for the day. So with that, I will conclude and take any questions you might have. Thank you for your attention. Lots.
The 10,000-hour goal, is that like a journey to Mars in day? It's about 13 months, I think.
Yeah, that's kind of what the thought is, plus margin. It's also just a round number. But yeah, but yeah, it's the right order of magnitude. Yeah, go ahead.
Is there any interaction between navigation and transmission systems, like on a satellite?
Yeah, absolutely. Yeah. Oh, sure, yeah. So the question was, is there any interaction between the thruster element and the navigation or communication systems? And specifically, I think you're referring to RF interference, radio frequency interference. And the answer is yeah. These devices, because they're dynamic, actually emit a fair amount of radiation. It turns out that it's not prohibitive, and they do a lot of characterization before they put them on orbit. But yeah, they do emit, and they can actually emit in the gigahertz range, so that can pose a little bit of a problem. Yeah.
Would you use Xeon? Xeon's expensive.
Yeah.
Why Xeon? Could you use something else?
Yeah, you can use something else. Xenon has a lot of different advantages, and it's kind of the traditional propellant for electric propulsion systems. One advantage is that it's very heavy in terms of noble gases. And the reason why heavy is a significant advantage is that if you send your propellant out too fast, you have this trade-off in terms of what they call the thrust-to-power ratio. So the actual thrust of a device for a given level of power will decrease, which means that if you have a higher exhaust velocity, use something like helium or hydrogen, your transit times will become much longer. Though, of course, you would save in terms of propellant. So Xenon has that ability to kind of temper the high exhaust velocities you can achieve with these devices. Xenon has other advantages in terms of the kind of ionization losses with respect to mass. So you have less of a efficiency hit in terms of actually ionizing the gas using xenon. And the last one is that it's not corrosive. Because it's a noble gas, it doesn't interact with the walls of the chamber. So if you use something like oxygen, like an air breathing system, it could ultimately combine with the poles, which are made out of iron. I didn't mention that, and it'll rust them right away. Yep.
You're running right now with a three-channel system.
Right.
Is there any theoretical limit on how many channels you can put in to increase output?
No, there's no theoretical limit, but it turns out that there's an interesting trade, which is as you increase the effective number of channels using kind of known scaling laws, the mass increases. So about 3 or 4 channels, there's a minimum of the mass per power. That's using known scaling laws. If we do something a little bit more exotic, maybe we could increase the number of channels, but that's the next generation. Yeah. Yeah, in the back again.
I think you said that the weight massless is like 200 kilograms.
Right.
What makes up that mass? Is there any way to reduce?
Yeah, so the primary mass driver on these devices is the pole materials, which serve to guide the magnetic field, and those are made out of iron. So there have been some mass-saving measures already taken on these devices where they've honeycombed in some parts of the pole, so they've cut out material where it's not necessary for guiding the magnetic field. And you might be able to try some more exotic honeycombing techniques to achieve that. And that's actually something that we're looking at in the future. But right now, the mass is, in terms of other propulsion systems, it's pretty competitive, mass per kilowatt. Yeah.
Unfortunately, iron's a pretty good material for that kind of stuff. If you use something like ferrites or whatever, it's just about as heavy now, it's really brittle.
Right. So there's an increasing trend to move to hyperco, which is a more advantageous material in terms of saturation limits, but it has kind of comparable masses. Yeah. Yep.
Can the high electric field strength be used to help shield humans from the solar wind?
Yeah, that's an interesting idea, and in fact, totally unrelated to this. But if you go down to the Space Propulsion Research Lab at the University of Michigan, they have a concept where they use very high electric fields to do exactly that. The challenge with these devices is the electric field is contained within a very small volume, so it doesn't extend far enough downstream to do that kind of shielding. Yep.
You've spent a year very, very gradually speeding up this ship. You're going to take another year to very, very gradually slow it down so it can get run.
You got it. Or you just do something like aero braking, or you use a chemical propulsion system to impulsively decelerate.
And then how are you going to get it off the surface of Mars?
Never. You would never use these systems to launch off the surface of Mars. They would actually never descend into the gravity well. You'd probably have a detached ascent vehicle that goes down. Yeah.
You're saying about, 6 or 8 months to get to Mars, and the technology as you're aiming for?
Yeah.
What are the thoughts about combining that with conventional chemical propellants to use chemical propellants to initiate the thrust in their direction to Mars, and then use those to increase your acceleration on the way out, and then just reverse them, which just goes up down and you approach the planet?
Yeah, that's a great idea. They call those hybrid architectures, and they take many different forms. And one is, for example, to accelerate at to C3, so you get escape speed, and then you use electric propulsion, or one is use electric propulsion to set up the vehicle and use chemical rockets to boost it out. So there are some mass and time savings to do that. I guess I'll go out on a limb and say that I think that the time requirements are still on the order of 6 to 9 months, but that's something they look at and optimize from a mission trajectory perspective. But yeah, you're exactly right. It's kind of an exotic thing and interesting to look at. Yeah.
Do you have any problems with any harmonics between the 3 channels?
Yeah, sorry, I'm not repeating the questions. Totally. Are there any problems with harmonics or interactions among the channels? And the answer is we don't know. They do appear that they interact, but not in a necessarily bad way for the thruster. And in fact, right. And in fact, it turns out that the thrusters can help each other. And the reason why is this: the thruster channels themselves, they're very good ionizers, but they're not perfect. So if you put in a certain amount of gas, maybe 95% of it turns into plasma, but 5% leaks out. And some of that leaking gas will leak out and get re-ingested by the other channels, and now it becomes free propellant. So it can actually recycle a little bit of the propellant. And we've been able to demonstrate, kind of theoretically, it's a semi-empirical equation showing that you can get a boost in performance that way. Yeah, we'll just work our way back.
What about, leaving Mars,
Yeah, that's true. So the thruster would definitely turn on, there's no question, but you still have to overcome the gravity well, which is only 1/6 of the Earth's. So effectively, returning to that example of a book, right? The thruster would be able to lift a book up if you put a book above the thruster. But remember, the thruster itself weighs 250 kilograms, so it wouldn't be able to launch itself. Now you have to add the power supply, which adds several hundred additional kilograms, so it would never be able to sustain its own weight. Yeah.
Speaking of that, which power thruster did you say could be used to lift a piece of paper off the ground in a vacuum? 40 kilowatt?
No, 5 kilowatts.
5 kilowatts?
Yeah, it's 300 millinewtons.
If you took that 5 kilowatt thruster out of the vacuum, would it lift the paper at all?
No, it wouldn't even turn on, and the reason why is the ambient environment would prevent a breakdown from occurring. Yeah. So the densities inside these devices are about 6 to 7 orders of magnitude lower than atmospheric.
So it's got to be in a vacuum to even turn on.
Right, yeah. People are looking at air breathing systems. It's actually a pretty new concept, but even those would only work at very high altitudes. Yeah.
I have a very unusual question. A couple years ago, I read an AIAA paper on NASA's test of the EM drive.
Sure.
What do you think of that?
Yeah, so I know Dr. White fairly well, who is the progenitor of that particular concept. Testing. I don't think he actually came up with a microwave cavity. So we've had some discussions, and he's presented in papers before. I guess I'll reserve an actual opinion about the workings of the technology or not, but I will point to recent studies that were done in Europe, which demonstrated that this particular microwave cavity doesn't appear to generate thrust at all, which is kind of consistent with the physical understanding of those devices. In order for it to operate, there would need effectively be new physics, which I'm not sure exist or do not exist. Yeah. Yeah. Yeah.
Yeah, one other quick thought. You were talking about one of the challenges as far as doing this test of like trying to guarantee that you can keep that vacuum chamber operating for a year.
Yeah.
I'd be like, all it takes is one power outage, and then your turbo pumps don't run anymore, and then you're done.
Oh yeah, it's an incredible challenge, and for the next the Dawn mission, they actually did a 30,000-hour demonstration test, and effectively what they did is whenever they needed to rehabilitate the chamber, they had moved the thruster into a smaller compartment and wall it off with a kind of airlock, yeah. So greater minds than I have really thought about how you do these things, and they're still thinking about how you do lifetime demonstrations of moderate power systems. But you're absolutely right; it's a logistical challenge, which is incredible. Yeah.
Would it not be feasible to take it to the ISS and run it for a year there?
Yeah, and there were a couple programs looking at putting electric propulsion systems on the ISS. So this is getting a little bit out of my element, but kind of my understanding there are a couple limitations. One is that you have to be very careful about what you put on the ISS because there are people there. And so now we're sending very charged particles away. And number two is that even the ISS, the ambient atmosphere on the ISS is still orders of magnitude higher than vacuum because of outgases. So it's not like you could breathe it, but it's still it has its own atmosphere. Yeah.
You run this thing in the chamber, assuming you have the cameras inside, does the xenon gas actually emit an exhaust where you can see it come out or no?
Yeah, so those are kind of the pictures I was showing. What you're seeing are excitation lines primarily from neutrals. So the electrons will impact some of the neutral lines and kick electrons up to higher orbitals and de-excite and emit photons, and that's kind of the light you're seeing. And you're seeing some ions as well, but that's kind of that blue glow for xenon. If it ever turns orange, you know you're in trouble because orange is air. So, yeah. There's one in the back, yeah.
So you mentioned the price of large quantities of xenon. Is the chamber able to recycle what's used? You mentioned also that you don't want much xenon to be in the chamber while I guess the thrusters are firing.
Yeah, so the question was, can you recycle some of the xenon? And the answer is yes. So the way we pump right now in that facility, it's cryogenic. So when you get down to low enough ambient pressures, you can't use conventional kind of roughing pumps or scrolling pumps. You need to be a little bit more clever about how you do it. And actually, it's not clever. It's pretty simple. It's just expensive, which is you take a surface and you cool it down to cryogenic temperatures. So we have these plates, which actually you can see in this picture. So those copper surfaces in the background, those are cryo-cooled by refrigerators down to 30 degrees Kelvin. So the idea is that the xenon will random walk its way through the system, and then we'll hit that surface and freeze to it, and that's how we remove it from the atmosphere. So now you have these surfaces covered with xenon, and when we want to, we can warm them up. We'll shut the thruster down, warm them up, and then the xenon will re-emit from them, and then we pump those away with a roughing pump, store it in a bottle, and send it out to get cleaned. So the answer is yes, we can recycle it, and I don't remember what the conversion rate is, but we get most of the xenon back for a substantial discount. Yeah.
Does the xenon have to be under pressure when it's fed up there?
Yes, it does. So typically, the bottles themselves are about 800 psi, though that decreases, of course, as they run out. And then we regulate down to 30 psi to go through the lines. And then actually at the thruster inlet, it's usually about 1 pound per square inch going into the thruster itself. Yeah.
So you mentioned that you get there's been some reuse of the material with the X3. What about conceptually stacking? So, because you mentioned that the xenon reforms at the tail, right? What about stacking so you could collect that and use that in the next one? What do you think about that?
Well, so I think that's a clever concept, but you probably run into momentum conservation issues, which is that if I put a collector downstream, which has to be attached by the spacecraft, I'm pushing the thruster this way, then that xenon hits the collector and pushes me in the opposite direction. So you have 100% reclamation, but zero thrust. Yeah. Okay, well, thank you again. Thank you. Yeah.
That's the